All right, so 1-3 is titled Algebraic Expressions. So we're going to look at different expressions and determine how many terms there are, the degree, what type of polynomial they are. We'll do the sum, the difference, we'll find the product, and then we're going to do some simplifying, and then like I said, we'll touch on some factoring today, and then we'll do a bigger factoring review on Tuesday. Okay, so a monomial has one term. Emily, what was your monomial? 5x, great. Okay, and then I wrote 1/2 x to the 5th, so I have my two examples there. Okay, so you're just going to have one term for the monomial. Okay, a binomial is a sum. It could also be a difference. So you could have something like x minus 3, okay, or you could have 2x squared plus 5. Doesn't just have to be x. Okay, and then a trinomial is a sum. Jake, will you give me one of your trinomials?
X squared plus x plus 2.
Great. Okay, and then I'm going to give you guys one as well. X cubed plus 2x squared minus x. Okay, a lot of times we're trying to factor these. Do you guys remember what we'd factor out if you had a trinomial that was x cubed plus 2x squared minus x? Yes, you factor out the x, which is the GCF. Okay, and then a polynomial is a sum of not monomals, but monomials. Words were hard for me, I guess, when I was typing that, so we'll use switch that. And I'll give you one. It could be x cubed minus 2x squared plus 5x plus 1. Okay, and really all of those are types of polynomials. Okay, and then it could be, I said to do 2, so x to the 5th minus x to the 4th plus x cubed minus 1. And I just did 2 polynomials for 4 terms. Okay, so how do you find the degree of a polynomial? Do you remember that? What's the degree? Like the degree of this polynomial is what? Yep, and the degree of this one? 5, because that is the, yep, it's the highest exponent. Okay, so it's the highest exponent, and then I'm going to specify of the variable, because you know sometimes they'll try to throw one in there to trick you, like they'll have 2 to the 6th, right? But 2 to the 6th is a number, 64, so it wouldn't be the degree. Okay, so we're going to do a trinomial with a degree of 4, a binomial with a degree of 1. Will you write down an example of each of those for me? A trinomial with a degree of 4, a binomial with a degree of 1. All right, Kate, will you tell me your trinomial with degree 4? Great. And then Leo, what'd you get for a binomial of 1? Or, sorry, binomial with a degree of 1. 2x and then, great. Okay, and then the operations that you're going to do with polynomials, you're going to be adding and subtracting. Just make sure when you are adding or subtracting that you are only combining like terms. And if they are like terms, they will be the same variable raised to the same power. Same variable raised to the same power. Okay, which means if you have an x squared and an x, you couldn't combine them. Okay, or x to the fourth and x squared, we can't add those together. We can multiply them together, okay, but we can't add or subtract those unless they're both x squared or they're both x to the fourth. Okay, the next one says, if we're subtracting polynomials, what do we need to remember about the minus sign? So that would be if you have a problem like this. X squared plus 2x minus 3x plus 1. Okay, so go ahead and try that. Okay, so what do we have to do with this minus side here? This minus sign. Yep, you always want to distribute that negative. Okay, just to anything that's behind it. So it becomes a negative 3x and a positive 1. And then you can combine your like terms. So you have x squared minus x plus 1 would be your final answer there. What's that? Oh, sorry, minus 1. And I didn't distribute, and we just said that's what we have to do. Come on now. Thank you. X squared minus x minus 1. But that's why I gave you the reminder, right? Because it's easy to forget about that with the second one. You want to make sure you apply it to both. All right, and then the other thing we want to remember is how to multiply when you have polynomials. So the product, you're going to use the distributive property repeatedly. Okay, so when you're finding the product, you're going to use the distributive property. Repeatedly. If you have two binomials, we know that that's called FOIL, right? So that's when you have the two binomials in particular. And when you're multiplying, you also have to use those laws of exponents, right? If you do x squared times x, it's x cubed. So when I'm talking about the distribution, that would be if you had something like this. You had x plus 2 times x squared minus x plus 1. Do we remember how to do that? So, yeah, what are we going to distribute first? Yep, let's distribute x to everything. And when it says use the laws of exponents, what that means is this is going to become x to the third, x to the second, so be 1x. And then one thing I like to do when I'm doing problems like this is I like to line up my like terms to make sure I only combine those together. And then I just think it's easier to add them downward. You can make a big line if you like that better, that's fine. I'm just giving you some different strategies that you can use when you practice on your own. Okay, and then we have these special product formulas. When you're doing these formulas, a lot of times you are just going to end up foiling. So if you were to FOIL a plus b times a minus b, if you were to multiply those together, okay, we would do a times a first, and that would be a times a would be a squared. And then what would happen with the middle terms, the inside and the outside? They cancel each other out. You have AB minus AB, and then what's B times negative B? Negative B squared. Okay, so you don't have to use this formula. The book gives you this box of the formulas. This is just another tool that you can use, but you don't have to use this. If you have something that's squared, right, you can use this formula, this pattern I'm going to show you, but you could just write that out twice and then you could FOIL it, right? So this isn't something that you have to use. This is just a special pattern that happens every time. So it's the first term squared, it's double the product, and then the last term squared. The first term squared, double the product, the last term squared. Because this is minus, that's why double that product is minus. Okay, again, you can just use FOIL when you are doing this. Okay, and then you have the cube of a sum, and then you have the cube of a difference. Okay, so one way that you could do this, the cube of a sum, you have a plus b to the third power. Let's do an example together up here. Okay, let's say we have x plus 1 to the third. You can use this pattern I'm about to show you. I'm going to remind you how we did it last year. But if I have something that's simple like this, I would probably just write it out as x plus 1 times x plus 1 times x plus 1. And then how do I go about multiplying those together? You can just pick two of them and FOIL, right? So it doesn't matter if you do the first two or the last two. I like to do the last two first. So if I FOIL, this is another time where I could use this, right? It's x squared. 1x and 1x is 2x. 1 times 1. I still have this x plus 1 in front. So now I distribute. So if I distribute x to everything, I have x cubed, 2x squared, and x. Why don't you go ahead and line it up after you distribute the 1 and then get all your like terms together? Okay, I know for some of you I'm probably going too slow, for others of you I'm probably going too fast. So just know that I'm trying to be somewhere in the middle, giving you guys enough time to try this, okay? Okay, and then we're adding straight down. And what we've just done is we're going to prove this pattern. So when you do this, you're going to get a cubed, a to the third. Okay, and this example, x was your a value. Okay, the next term is always going to have a coefficient of 3. So it's plus 3a squared b. The next one is always going to have a coefficient of 3. Again, it's if you have the coefficient of 1 there, where you'll have the 3. Do you guys remember what the coefficients relate to? So last year we did binomial. In Algebra 2H we did binomial expansion. In Algebra 2 you also did binomial expansion using this very special thing. Yeah, Pascal's triangle. Okay, so these coefficients match up with what row in Pascal's triangle? The third row. Right? So remember we would do 1, 3, 3, 1. And the first one we would start, right? So you have a to the third, a to the second, a, and then what's a to the 0? 1. And then it would be b to the 0, which is 1. B to the second, b to the third. That's where this pattern's coming from. Okay, that's where this came from. Okay, and if you're like, oh my gosh, I do not remember Pascal's triangle, why are you doing this to me? Just use this strategy. Okay, you do not have to use Pascal's triangle. The most you'll have to do today is the cube, and you can FOIL, then distribute. Okay, got that? All right, and then you can apply those formulas using substitution. Again, I just told you a lot of those are intuitive and you won't necessarily look at the formula, you will just do that naturally. All right, when you multiply a square root by itself, the result is the radicand, that value underneath. Okay, so if we're doing the square root of 8 multiplied by itself, what should we get? 8. Right? Root 8 times root 8 is 8. We also know that that comes from this, right? The square root of 64. This can also be applied when you have variables. So when you have the square root of 2x times the square root of 2x, okay, according to this rule, we know it's going to be what? It's just going to be 2x, right? Well, that comes from, if you're multiplying 2x by itself, isn't that 2x squared? And what happens when I take the square root of something that's squared? When I take the square root of something that's squared, what happens? Yeah, you just have the radicand or it undoes that. They're inverse operations. So if I have the square root of y plus 1 times the square root of y plus 1, my answer is y plus 1. Okay, so we got that pattern. It's second nature now. Yes, Miss Whipple, but what we really want to do is go home and take a nap. Okay, so when we're factoring, a lot of times we have to take out the GCF. So when I say GCF, I mean good cook good Francis, or what? What does this mean? Yes, greatest common factor. Okay, and a factor is just a number that divides into it evenly. Okay, so it's the largest value that divides evenly into all terms. The largest value that divides evenly into all terms. Okay, and I emphasize all because sometimes it goes into just a couple of them. And if that's the case, you can't take it out of all of them. It's not the GCF. Okay, so I want you for A and B, go ahead and write down what the GCF is. Okay, GCF can have a number and variables in it. Okay, so I start with the number. All right, so or 6 and 16, what's the largest value that comes out of both? 2. Okay, so 6 and 16, 2 is the largest one. Now let's look at the x's. Here I have x squared, here I have x. So is the GCF x squared or x? X, because you can't take 2 out of the 1. Y to the 6th and y to the 4th, you would take out? Which one, 6 or 4? 4. Okay, so this is your GCF. Okay, and then I want you to factor what it would be. So if you take out 2xy to the 4th, write what you're left with. Okay, so be on this page with me. I want you to factor that out. Practice dividing that with your GCF. All right, and then go ahead and do B. And then I want you to factor it as well. Okay, so when you factor out, you're dividing. So 6 divided by 2 is 3, x squared divided by x is x, y squared, and then 16 divided by 2 is 8, x divided by x, 1, this is 1, so this is going to be what you would get when you factor. Okay, and then John, what was your GCF for B?
XY.
Nice. Okay, so your GCF for B is XYZ. So when we factor that out, okay, what we're doing is dividing. Now, the reason why you can't take any numbers out, 2 goes into 2 and 6, 3 goes into 3 and 6, but nothing goes into all 3. So you're going to keep this as -3. Okay, and then it would be x to the 4th. The y's would cancel, the z's would cancel, and then plus 6. The x's would cancel, the y and the z would cancel, and I'm okay if you leave it like this for this one. And then if you divide, you would have x squared, y, z squared. Okay, so that is factoring with your GCF. We're going to go over the factoring rules book real quick to just jog your memory. Remember, you always want to look for those common factors first. And if I have taught you factoring before, you know, to help people remember, I always say the rules of factoring are like the rules of dating. So the first thing you do, see if you have anything in common. You find that GCF, those common terms. Okay, and then the next thing you want to do is find out what makes that person special. And in factoring, the factoring world, we're going to look for special patterns. And we're going to go over some of those patterns together. And then the last thing is we'll just guess and check, right? Go out, see if you have fun. As a disclaimer, if you do not have fun, it is not Miss Whipple's fault. I cannot be sued for any bad guess and checking. Okay, and then we can always check our answers using the distributive property or FOIL, okay? Which we are also going to do today. All right, so the special formulas. I know you all probably just have this special, a favorite special formula, right? How of you, your favorite is difference of two squares? That's my favorite. I think it's the easiest to remember. You have a squared minus b squared. That's going to factor into a plus b, a minus b. Okay, that's also the most common special pattern. The next two, you aren't necessarily going to have to know these patterns. When you go to factor, you are naturally going to unfoil, right? These are called perfect square trinomials. So you usually have a perfect square at the start and a perfect square at the finish. So you'll probably recognize that. Okay, but the perfect square trinomials you don't have to know by heart. You'll end up factoring them into a plus b and a plus b. If you have the same factor twice, you can just call it a plus b squared, the whole quantity squared. Okay, and a minus b squared. Okay, and again, you can just factor those by guessing and checking. When you notice they're the same, you can write them as one term. Okay? All right, now the sum of cubes and the difference of cubes you do have to know. You have done this before. Oops, plus. And this one's the difference. Now that some of you even remember what they are. Okay, so when you are doing this pattern, you start with the cube root of each term. So what's the cube root of a to the third? A. Cube root of b cubed, b. Okay, and then in the second set of parentheses, we have a trinomial. So it's a squared, and then it's minus the product of a and b, and then you add b squared. Okay, the last one is always plus because it's a square, right? Your square term is always going to be plus. Okay, based on that, do you guys think you can fill in what the difference of cube is? The difference of cubes? Is some of that coming back to you? With the difference in the sum of the cubes? Okay, so this is going to be subtraction. It's a squared. This is plus ab, and this is plus b squared. Again, remember I said if it's squared, it's always positive. Positive times a positive, negative times a negative. Okay? All right. Now, when you're using these formulas, if they have perfect squares and perfect cubes, we have to know what they are. Remember, a perfect square is just when you take the square root, you get what type of number? Take the square root, you get a whole number. Okay, same thing with perfect cubes. If you take the cube root, okay, you're going to get a whole number. Okay, so starting with 1, we'll list the perfect squares up to 10 squared. And to generate that list, we're just going to square. So we're going to do 1 squared, 1, 2 squared, 4, 3 squared, 9, 4 squared, 5 squared, 6 squared, 7 squared, 8 squared, 9 squared, 10 squared. Oh, do we know 11 squared? What? 121. I'll put these on here for funsies. Do you guys know 12 squared? Yeah. 13. 14. 196. That's how I remember these two, is the two numbers are switched, and then 225. So we'll just get up to 15. Okay, but with this one, we'll only do up to 10. Okay, so with the perfect cubes, again, 1 squared is 1, 2 squared is, or 2, sorry, 1 cubed is 1, 2 cubed is 8, 3 cubed is, what's 4 cubed? 64, what's 5 cubed? Okay, and I know the ones after this are hard to remember, so that's why we're writing them down so you can recognize them. 6 to the third is 216, good. 7 starts with a 3. You guys remember that one? 3, 4, 3. You'll know this one when I write it down. 512. Do you guys remember working with that number last year at all? And then we don't work with the 9 cubed a lot. Yeah, 729. And then what's 10 cubed? 1,000. Okay, also variables can be perfect squares or cubes. If we're doing a perfect square, we have x squared generally, but these are all perfect squares too. X to the 4th, x to the 6th, x to the 8th. What's the square root of x squared? X. What's the square root of x to the 4th? X squared. What's the square root of x to the 6th? X cubed, and we get the pattern, right? So what do you notice about all of those exponents? Yep, they're all even because they're all multiples of 2. Okay, and then the most common perfect cube you'll see is x to the 3rd, because when you cube root that, you get x. But you couldn't have x to the 6th, right? You get x to the 6th by multiplying x squared times x squared times x squared. You get x to the 9th, x cubed times x cubed times x cubed. What do you notice about those exponents? Yeah, they're all multiples of 3. You could also say they're all divisible by 3, but they're not all odd, and they are not all I guess even, because there's only one that's even. All right, and then I want you guys to look at the back here. We're going to be doing some factoring by grouping terms. Okay, can you guys fill in that blank there with the factoring by grouping? Okay, so can they sometimes or always be factor grouping terms? What do you think? Sometimes, right? Your English teachers have trained you well. It's rarely going to be always, right? There's usually some exception to the rule. Okay, and then just so you know, up here, in case you're doing your homework and you're like, oh my gosh, why did some of these problems have fractional exponents? Okay, I'm not assigning you any of those, and you won't be assessed on it. If you are curious about it, there is an example of your book, and you're welcome to look at that and explore it. You just don't have to know how to do it for this. Okay. When you are factoring, it's best to make sure your polynomials in standard form. And then we'll group the first 2 and the last 2 together so that we can take out those common factors. Okay, so we're going to factor I said common factors, but I should have said common terms so it doesn't sound so redundant. So that is that GCF. Then, if what's left inside the parentheses is the same for both groups, then we can factor out this expression because it's a common term. Okay, so it has to be the same for both groups. And if it is, we factor out this common term. So it's like a double factoring there. Okay, and I see some of you guys already started on this to see if they can be factored using the grouping method. And we want to factor it completely. And then if it can't be, we're just going to say why. So we're going to group the first two together and group the second two together. If you remember how to do that, go ahead and give it a try. The first two, we're looking at the second two. All right, so we should have taken out an x squared here, which is going to give you 2x plus, don't forget the plus 1. Because when you divide it, x squared divided by itself is 1. And you can double check that with distribution. If you didn't have the 1 there, it would just be x squared times 2x, which would only give you the 2x cubed, okay? And then because you want these to match, this would be a negative 3. So this would be 2x plus 1. Again, I do a quick check in my head to make sure when I distribute that goes back. And then what we're doing here is we're saying, look, this is multiplied by the same value. It's just that it happens to be a binomial instead of a monomial. Okay, so when we write this, I will usually write this one first, even though what you're factoring out is the 2x plus 1. And this is going to be your final answer. Okay, you can always check to make sure that is correct by multiplying or foiling it back. Okay, this does not go from like 2 to 1 and this just disappeared. What we did is we rewrote it using the distributive property. Because if you do x squared times this, you get the first term. If you do negative 3 times 2x plus 1, you get that second term there. All right, and then we'll start by grouping in part B. So again, we're taking out what they have in common. So 4 and negative 8, I can take out that 4. I can take out x cubed, which is going to leave me with x minus 2. For 2x and 2, I can factor out a 2, which is going to leave me with x plus 1. So these are not the same. Therefore, you can't factor by grouping. Okay, if they're not the same, you cannot go any further. Okay, so we are just going to factor this, and the only way you can factor this is by taking out a GCF. So if we're looking at this whole problem, the 4x to the 4th minus 8x cubed plus 2x plus 2, what is the GCF there? 2. So this is going to have a different answer. So when you divide by 2, you get 2x to the 4th minus 4x cubed plus x plus 1. This would be your answer. This is factored with the GCF. Okay, and then I already told you that you can check these using FOIL or by just multiplying them. Okay, so our explanation is that you can multiply, you can FOIL. Okay, so choose one to check below. We're going to do the first one since the second one couldn't be factored with grouping. Okay, so if I take x squared minus 3 times 2x plus 1, okay, for A, that's my solution. If I FOIL that, I like to write out like what I'm multiplying. So x squared times 2x is going to be 2x to the 3rd. And then I like to do the inside, which is negative 6x, the outside, which is positive x squared. And then I'm just going to put those in standard form. So I'm going to put the x squared first, and then the negative 6x. And then negative 3 times 1 is negative 3. So this would be my answer. I'm just going to verify that it matches what I was given for part A. Okay, and if it does, then we did it right. So that's another way that you can check. If you were to write 2x plus 1 times 2x plus 1, you'd have to multiply this by 2x plus 1, and it would not go to what was given for A. Okay.